Okay, you may start.
Okay, thank you.
Yeah.
Okay. Hello, this is Yao Chu from HKUST BIM Lab. And my presentation title is Automated Ventilation Ductwork Design from BIM Data. Okay, as we all know, the building accounts for around 30% of global energy demand, so it's very important to save the energy in the building section. And the ventilation system is one of the major source of building consumption, which directly affects the indoor air quality and the thermal comfort. And the system energy mainly determined by the system pressure drop and the material cost. And the duct design requires a simultaneously consideration of topology, duct size, and the fluid dynamics. Okay, and the traditional ventilation ductwork design is divided from the three parts: the topology generation, the size determining, and the evaluation. So this method, this is a one-way sequential process, and it breaks the connection between topology and the size, so which will lead to the local optimal. And from the paper the paper in 2024, we can see that the different kinds of category CFD category also consumes consume the computation time from several minutes to several days per evaluation. So, and for our generic design needs, the heuristics algorithms require the evaluation of more than 1,000 candidate solutions. So it will lead to enormous computational time cost, and so it cannot support the large-scale interrupt optimization. And for the limitation 3, we all know the existing method for the generative design is rule-based without the physics metrics. And from the paper in 2025, the anti-column optimization parallel search is more focused on the graph topology rather than physical metrics. So the limitation 3 is the layouts generated solely by the geometric rules often have poor performance. And for my research, the objective is to address the limitation discussed before. This study established a graph-based automated ventilation ductwork design framework and introduced the PA surrogate evaluation and achieved the joint optimization of the topology and duct size. The phase 1 is the data preparation. First is extract the data from BIM model and construct it into a graph-based representation, and then describe it into the escape graph. From the phase 2 is the optimization process. It uses the joint design generation to design the ductwork and use PN surrogate model to evaluate. When we got the evaluation, we can optimize it with the result and get to achieve the multi-objective fitness calculation. And then to the phase 3 is the final output and validation. This is the BIM model. We use Dynamo to interact with the BIM environments and instruct the boundaries, the obstacles, and the ventilation duct, and project the 3D space onto a 2D coordinate. And for the graph representation, when we got the physical geometry design, we use the spatial mapping and feature extraction, map it into the node and the map. It has the shaft feature vectors, the diffuser feature vectors, the node, and the edge. And then when we got the graph, we define the minimum bounding box and the obstacle expansion, the orthogonal extension and the topology pouring to get the escape graph. And for the the phase 2 optimization, first is the joint design. For the escape graph, which is described into the node and edge, what we need to do is choose the edges and give attributes to it to realize the objective of ductwork design. First is the topology algorithm is disaster-like shortest path expansion with a TER penalty and a small randomness. And the sizing algorithm is use the when we got the topology connection, we can get the downstream diffuser number and calculate the duct size. Use the formula shown on the slides, and this will determine the objective, and the objective will give feedback to this two parameter. And this is to replace the CFD and achieve second level prediction. I proposed the PN surrogate model. We input when we input the data, the surrogate model will predict the pressure field and the airflow field. And use these two parameters, we can calculate the data loss and the physical loss. Use this tool, we can give the total loss to the optimizer to minimize the total loss and give the update the width, and finally get the best design. And for the when we got the algorithm output the surrogate parameter font, we use Pandapipes physical silver to validate the output Pandapipes product font and select the final output optimal design based on the preference weight. And this is the result of 3 cases. The first one is the simple one, and the second and third one is more complex. You can I use the PN method and the CN method to predict the node pressure and from the of the 3 cases and contrast it in the slides. And the comparison between the different neural networks, we can see that the accuracy drops from both the models as the complexity increases. But in the simple layouts, the CN is better than the PN because it's easier direct data mapping. But in the complex layout, the PN shows superior robustness and accuracy because the physical laws prevent overfitting the complex networks. And for the I also use I use 6 different methods to show the to design in the 3 cases. This is the case 1. Is the baseline, the simulation method, the heuristic, CN, PN, and the formula. And this is the 6 results of the case 2 and case 3. Yeah, and the result is shown on the right table, the comparison between different methods. And for the we can see from the table that the heuristic is fast, but it has the yield the worst pressure drops. But for the comparison between PN and CN, they both fast, but the PN is the reduced pressure drop by 20.6% than CN, and the PN for between the comparison between PN and the simulation method, PN match the accuracy within 10% difference of the simulation method, but is 96% faster than the simulation method. And compare the initial baseline, the manual method, the PN framework achieve average reduction of about 25% in the both material cost and pressure drop. And for the conclusion, my research established a graph-based automated ventilation duct design framework and proposed a topology-aware PN surrogate model, introduce geometry aware heuristic search and propose a joint optimization strategy. And it also have some limitations. First, it's limited to 2D layouts, and it assumes the constant airflow and focus on only the ventilation system. So in the future, I will use the GN for 3D spatial coordination and integrate the real-time environment data for the demand control ventilation, and couple the thermal and acoustic fields to develop generative algorithm for multi-physics core design. Thank you for your attention.
Thank you very much. Any question to